Go stop on your desk for a minute. So let's do the electron configuration of aluminum. Just aluminum. I'm ready when you are. 1, S2. You're looking at your periodic table. You're following it across, okay? 1, S2. 2, 2p6. That gets all the way to neon. Where's the record here? 3s2. 3p1, right? 3p1? 3p1. Okay, that's where we are. We're at aluminum. How many valence electrons does aluminum have? Valence electrons. 3, because they are in the valence shell, which is the very outside shell, which is the third shell, and that third energy level is the last one we reach. And if you count them up, there's 1, 2, 3. 3 valence electrons. And so, like this, you're going to have to be circling, like I'm telling you what's on your previous ones, okay? You have to circle the valence electrons on 1 or 2 examples in your test. So, is that close to 8? No. So that's, that's on the, before the breaking point. You can either go back or you can go forward. Going back means you lose electrons. Going forward means you gain electrons. So is aluminum going to gain or lose electrons to achieve octet in its outside state? Lose. And so actually, if you lose this entire energy level, meaning those 3 electrons, that's going to give you an overall charge of what? Yes, aluminum 3+, because you've now achieved octet in your last energy level by losing electrons. And the way you can see that you've achieved octet is if I lose this third energy level, what's my valence shell now? Hold on, what's my valence shell? 1 or 2? 2. So the second energy level is my valence shell. And then look at it, guys. How many electrons are here? 8. So that's what I mean by octet. By losing electrons, you achieve octet because you back up to octet. Not that you've like miraculously taken away 3 and you're at 8. Like, what does that mean? It's backing up to the last octet state. So that's why everything has a very, very, very specific charge of forms, because everything has a specific number of valences. So that's the electron configuration of aluminum 3+, 1s2, 2s2, 2p6. Boom. So who does it look like? Neon. Good. Okay, do the same thing for copper. Write up the full thing for copper 2+. Copper. So copper's in the transition metal group. I'm ready when you are. Yeah. Yes. Yes. Noble gases are the cool kids that every element will end up at with their electron configuration. Yep. All right, so copper, 1s2. So the long one, okay? 2s2, 2p6, so that gets us to neon. Keep going. 3s2, 3p6, that gets us to argon. Okay, next. Whoa. 4s2, right? 3, right? So 3d. 10. Okay, so that's all the way over to zinc. Oh, sorry, lost it. Gotta go 3D 9 because we have to stop at copper. Okay, so some of us I think just Googled because there are specific exceptions to some of these rules. Those are advanced topics. We're learning basic stuff right now, so I'm not going to do advanced. I want to stick with, let's look at the valence shell just like we've always done. Where's the valence shell? 4. Yeah, the 4th energy level is the valence shell. That is the loose electron shell. That's the ones where you're going to be able to lose electrons or gain electrons, and nowhere else. So that's why copper, in this example, forms a copper 2+ charge, because how many electrons does it lose? 2. Those go away. So whenever you write the electron configuration for a straight up copper 2, you do blah, 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 3p6. Don't write that, and then you end in 3d. Do not take them from the 3d shell. That's not the valence shell. Okay? Copper can act a little differently in some situations, but that's what we're sticking with because we need to understand valence right now. Okay? The other one, P3 minus. Can you anticipate what electron configuration that looks like? Who does it look like? I turn this around because I can stand up some periodic table over here. Look into that way. Okay. There's phosphorus. If it gains 3 electrons, who does it look like? Argon. 1, 2, 3. So it looks like argon. So what will be its very end electron configuration? 3p6. Good. So it was 3p3 at phosphorus itself, but with these 3 extra electrons, it ends up at 3p6 because it gains them in those empty spots. Okay. So do we feel a little bit better about the ions now? Okay. Problem set 6. Questions before I take it? I was going to go over one section on the bottom. Consider the following elements. A, conductive, B, liquid, colored, and D, metalloids. The options were calcium, hydrogen, cobalt, aluminum, silicon, sulfur, and chlorine, right? Okay, how many of these were, A said, how many would be conductive? What is it actually asking? It's asking about something more than that. Which ones are metals? Right, okay, so I don't know what I'm looking at right now. Yes, 6. Oh, there it is, okay. So which of these are actually metals? So cobalt, what else? Calcium, yep, everything on from the staircase that way. What else? Aluminum, is that it? Silicon is actually a metalloid. That's right. Silicon. Where's the one with the dang little bridge on it? I was going to show you this. Well, it's hard to see. There's a metalloid.
Miss Emma?
Yes?
Could I have Eli Tumblr for dismissal? He should come down to the attendance office.
Yes, ma'am. Thank you.
Thank you.
Aaron, you do run off for just a second, okay? They called for you earlier. And that's already for you. Okay. Okay, on the metalloid line, that is going to be silicon. Silicon is not going to be a metal. It's a metalloid. Okay? So there are only 3 of them that are metals. B said how many of them are liquid or gas, likely. So what is it actually asking for? Which ones are gases, like noble gases? But I'm thinking just in general, which ones are non-metals, true non-metals. So which ones are true non-metals? Right. Hydrogen is suspiciously in the metal category, right? It's not a metal. Do not say it's an alkali metal, because we all know hydrogen is not a metal. That was a big misconception in a previous class. And then sulfur is definitely a non-metal, and then chlorine is definitely a non-metal. So there are 3 of these as well. Oh, and then, yeah. Put that in the box for me. Yeah. Thanks. 1, 2, 3. Did I write them all? Yeah. Silicon would be a metalloid, which is our last category. Silicon is the only metalloid. Okay? It's actually, this is what it looks like. So a silicon wafer. Okay? This is one crystal. Right? This is what solar cells are made of. They are conductive in a different manner than normal metals, but they're solid at room temperature simply because of this crystalline structure it's forming. So that's why I did not include it in B, where it said non-metals, liquid gas, because it's not a liquid gas. Okay. And then last one, which ones are colored? Which ones have colored properties? Only cobalt, right? So cobalt, because it's a what? Transition metal. You should know that transition metals exhibit color, and there are no more transition metals, so no more would exhibit color. Okay, anything else on here that you guys want me to cover? Yeah. Number 1 matching doesn't have. There are 4 answer choices. Omit that one. I'm going to take it as yesterday because I haven't fixed that on the answer choices yet. So there's only 4 answer choices. You only have 4 matches. Another one? Which in the columns were identical? Which categories in your big table were identical? So largest radius, meaning it's down and to the left, and most metallic, those are the same, and lowest electronegativity. Good. And then the others, ionization energy and EA were the same because they trend the same direction. So there should have been some patterns there. Yeah? Yeah? Okay. Hold on to that for a minute. Yes?
I don't know, like for 8, I don't have like for 8 on the chart, I got like I put not or like the high energy not.
Okay, so krypton is a noble gas, right? We're talking about, do you say ionization energy? Krypton and iodine. So krypton is a noble gas, iodine is a halogen, and krypton being at octet already is going to probably put up a bigger fight. It's farther over, and it's farther up. It's definitely going to have the highest ionization energy, not iodine.
I wasn't sure.
Because they're really close, right? But if you, well, they're invincible in terms of taking their electrons, meaning their energy is going to be really, really high. You can still take them, but you got to put forth a lot of energy to do so. Okay, PS6 and reading guide. I want you to hold on to your reading guide 25, because or whatever, because you can take your notes on that, so everything's kind of collect together and use some of the stuff that you've previously done. And instead of me going over first all your notes, I'm going to do this as a pairing activity, okay? So what we're going to do today is you're going to take some notes on a Google presentation. I'll move this QR code back over in just a second. And it's basic information about alpha particles, gamma particles, and beta particles, and transmutation, changing the protons, changing the nucleus. Also a little bit more about fission and fusion. We're going to recap for about 5 minutes afterwards to make sure that we're clear on how to write these nuclear decay equations. And then you're going to jump into Skittlium, which is a lab where we have radioactive Skittles, and then they decay to blankium. So the Skittlium is when the Skittle's on, the acid's on top, and blankium is when it is turned over. It's safe to eat when it's blankium, okay? So it's really easy, but it's a nuclear decay lab, and we'll do some analysis with it, okay? So find somebody that you trust. They will not get you off task, so we can get this thing done in class. There are Chromebooks set up. The link is under my website, and I'm going to put it right back up here. On my website, though, it is under Honors Chemistry Homework. But yes, pass up PS6. Hold on to your reading guide so that you can take notes on it. Here's the link for the nuclear chemistry notes. It says nuclear chemistry notes link. It's very specific.
On my thing, I forgot to say
I figured you're always on it. Thank you.
Thank you. Sorry.
You're good. I was confused. I was like, Avery does everything. Go to a Chromebook, give it a partner, take notes. Everything from nuclear together.
Miss,
Yeah?
we share a Chromebook?
Yeah, you're working together with one person. Yep. There are Chromebooks and there are desktops. If you're sitting right in front of a desktop, then I recommend you use a desktop, because if not, you're being greedy. Oh, I was like, where are my keys? Here, do you need? Okay, guys, so here's my general timeline. I'm saying 15 minutes-ish on notes, maybe 20, depending, and then you start your lab. We'll recap after that. Okay? Please start on to me.
Yeah.
You can edit? Oh, please don't, yeah. Please, no, like, make sure it's up.